All right. Hopefully everybody can hear me. I'd like to welcome you guys out to the SOLIDWORKS simulation. Some quick little tips and tricks. We can kind of get finished up in about 30 minutes. First, for some starters, my name is Steve Darcy. I'm an application engineer for Progression Technologies. And I want to make sure that you guys can hear me real quick. If you can, raise your hand. Let's make sure that the sound is going through pretty good. Okay, I see a couple of you guys raising your hand, so that's good. And let's go ahead and get started. All right, so some of the simulation products that we have, we're going to pretty much play in the SOLIDWORKS Premium area right here with some linear statics. We will show you a couple of 2D simplification. To do that, that's in the professional and the premium products, and just a couple other little cool tips and tricks to kind of get you where you need to be. So let's start off with the simple little bracket. So one of the things that I like to do is to simplify with configurations. So occasionally the actual model that you manufacture may have a lot of extra detail on it that we can pretty much neglect when we're doing our FEA analysis, our stress. So a lot of times I'll remove some small features. I've got some little fillets on here, some little chamfers, so we need to get rid of those things. And you really just have to make assumptions as to whether or not those are necessary features or not. You know, if they are, then we need to do something about them. Also, something else is instead of actually modeling up a washer, a lot of times I'll use the split face function. So I'll kind of show you how we can do that. And then in this case, the part is symmetric. So in a symmetric part, it's really simple to just slice that thing in half. And the main reason why we might want to do that is just because the less amount of mesh elements that we have, the faster it is going to solve. And then the last thing I'm going to show is if you can't figure out exactly where your higher stresses are going to be, and you need to find out where your mesh refinement is going to be, we can use tools called adaptive mesh to kind of get the job done. So I'm not big on the PowerPoint, so we're going to go ahead and switch right over to SOLIDWORKS. So here's my 3D part. And so the first thing I want to do is go ahead and create a configuration. And I'm going to go ahead and do this by scratch, and then we'll kind of go from there. So I'm going to add a configuration. Just call it simplified part. There we go. And so then all you have to do is come into the features and get rid of what you don't want. So I've got this extra little chamfer on here. I'll go ahead and suppress that. If I delete it, then it's going to delete it from the other configuration. So if I have a drawing off of it, then that's not going to be a very good deal. I need to go ahead and just suppress it just so it's for this active configuration. You can see I've got all these extra little fillets on there. So we need to do the same thing. We'll go ahead and just suppress those. And then also, if I know that this is symmetric, then I can do symmetry across the side of this thing. And I've already got a cut that I can just do that with. Now, you'll notice across the face of this, let me go ahead and turn off real view graphics. You can kind of see this face and the face right next to it. They are coplanar. They're along the exact same plane. But in stress analysis, a lot of times we want to break that thing up just to make sure that we have, if I want to put a washer or something like that on there, or signify I'm actually putting a stress or pressure across an area, and I don't want it across the entire area. So I'm going to show you how to quickly do that. I'm just going to start from scratch real quick. And I'll just sketch a little square block. And we'll just extrude it real quickly. And say, for instance, I want to have a hole in here. So I'll just draw out a circle. And so now if I want the pressure on the outside of this to signify like a washer or something like that, kind of what we do is we do a new sketch. We'll go ahead and draw a circle. And then that's it. Of course, I want to dimension it and everything. Then we're going to go to Insert, Curve, and do what's called a split line. So the split line is going to use the active sketch, and then you have to tell it what face you want to actually split. So it actually goes normal to the sketch. So I can split this face, or if I have a washer on the bottom, then I may want to pick on that back face as well. So when I hit OK, you'll notice what it does is it superimposes that sketch, and now I have a face that I can select that's going to be separate than the entire face. So that way, if I just want to push a pressure or a force on a specific area, I can use the split line to do that. So that's a really good technique to use. Keeps me from having to model up a lot of stuff. All right, so I've got my part here. I've simplified it. I've cut it in half because it's symmetric. So let's go ahead and run some stuff. I'm going to go to my symmetry configuration, and each of the different studies that you do are configuration specific. So I've got a standard one. I'm going to go ahead and just do a quick mesh on this so we can see what that looks like. And I'm just going to accept the defaults, and we'll go ahead and turn off our simulation symbols. So it's a fairly coarse mesh. The good thing is I do have at least 2 elements through the thickness of the material. So that's a really good tip. If I don't have more than 2 elements across the thickness of the material, then the strain is not going to be very good. It's not going to have the ability to actually bend across the thickness. So I'll get some pretty poor results. So anytime you're doing sheet metal parts and stuff, if you are doing as 3D instead of sheets, just make sure that you have at least 2 elements across the thickness. So here I've got 4. I'm actually pretty good on this one. So let's go ahead and run it. It doesn't take too long to run this guy. And I guess I should have showed you, I did put symmetry on here. So we do have a tool, a fixture specifically for symmetry. Make sure when you're doing symmetry that you select both of the faces, because even though if I just select on one face, it looks like it's showing me what the symmetric results look like. But that's not the case. Really what happens is at the actual node level, we're really just restraining the degree of freedom to actually go, in this case, across the Z direction. So if those nodes can't move across the Z direction and it expands, has to expand outward, in this case, the negative Z direction. So when you do symmetric, you got to make sure that you select on both of the faces. Because again, we're not actually doing like a mirror command or feature anything like that. All we're doing is all the nodes across that face, we're just constraining them so they can't move in that Z direction. They can move along the Y and the X, which is fine, but the nodes can't move along the Z. So they're static there. All right, so that looks good. I've gone ahead and run it. Another little tip and trick, I didn't put it on PowerPoint, but a lot of times on the stress results, let's go ahead and edit that. So just double click it. I usually go to the settings tab and I change the boundary options to the mesh. And what that does is it superimposes the mesh on top of the stress, in this case the von Mises stress. And here you can see I've got kind of a bit of an issue. So one of the questions a lot of people ask is, how do I know if it's a good resultant or not? And here I have, if I start to get splotchy results, then I know that my mesh elements are a little bit too large. So in the case, really what we're doing is we're color coding. We have a little color chart over here, and we color code the chart depending on what the average or what the actual stress amount is on each of the nodes. So if I know what the stress node is here, here, and here, then I color code it based on what the chart is. So here I get a little bit of an issue is I've got some very high stresses and then some very low stresses. So you'll see at each of these different little nodes, it's starting to get a little bit splotchy. It's a lot zigzaggy and stuff like that. So I want to make sure that the stresses are converged and I get a little bit nice smoother shape on there. Now there's 2 ways we could do that. Of course, I could just go to my mesh, right click and say apply mesh control, and then I can select on a face or something that I want to do the mesh control on. But sometimes if it's a simple part, then we can have the software automate that for us. So we have 2 little options that we can do that with. So one is called HAdaptive. To get to the settings, you just right click on your study, go to the properties, and then there's an adaptive tab when you're doing a static analysis. So I've gone ahead and turned on HAdaptive. So what this does is at each mesh element, it's going to go to a higher order mesh. I should say not mesh, but a higher element node. So if I do, I'll take a look at my mesh real quick. Let's create a mesh. So what happens here is I have what are called mid-side nodes. So I have a node at this little location. I have a mid-side node, so one right there, and then I have another node. So this is called a second order. A first order element really only has a node at the very beginning and a node at the very end. And these would be straight line segments. That's in a draft quality element. So what we're going to do in HAdaptive mesh is we're going to take the nodes that we have across these things and we're going to break it up. So the second order is, of course, I split it in half. So I actually have across each of these different lines, I'll have 1, 2, 3 different nodes. So what HAdaptive does is it finds out where the stresses are higher and it's going to break up these lines into more nodes. The more nodes I have, the more averages I'll have across there, and hopefully a smoother shape I'll get. So let's go ahead and run this. Now the way this works and functions is it is an iterative solver. So it's going to go ahead and run a loop and then another loop and another loop until it meets a certain criteria. And once it meets that criteria, then it's going to show us the results on there. So this one's a little bit better. Now you can kind of see that I've got a much more coarse shape here, but it's a little bit smoother as far as the gradients going from, you know, one color to the next. This is not my most favorite way of doing an adaptive mesh. My preferred method is a HAdaptive. So let's take a look at that guy. So again, let's right click on that. We'll take a look at the properties, and there's an adaptive tab. So in this case, we can tell it the maximum number of loops, because of course I don't want it to run to infinity. So I'm going to tell it to go, you know, maximum 5. But what I'm going to do is find out what the stress values are, and then find out the nodes right next to them, what those averages are, and I'll find out the difference between them. And if the difference between them is within 98%, then we can go ahead and stop. We can quit making the mesh smaller. If it doesn't reach that, if it's 97, then in those areas, we need to make the mesh element smaller. If we make the element smaller, then the nodes, we of course get more nodes as well. So let's go ahead and run this guy. So there it's running again. This one I like because you can actually see the mesh adapting. It's getting tighter and tighter. And it went ahead and ran 5 loops. And if we zoom in there, now you can see I get a nice smoother curvature going from, you know, blue to the greens all the way up to the reds. And I do have a very high stress in here. This is not a very good part. So I'll probably need to make it a little thicker or something, or change the material. All right, but you can see that the main thing is that the mesh is getting tighter in the areas where there's higher stress. The other nice thing I like about the HAdaptive is it does mesh coarsening. So areas that don't have as high stress, we don't have to worry about them as much, so it coarsens the mesh so it can still run quite fast. All right, so that's pretty cool. Some good ways to do simplification and sectioning, so we can use symmetry. All right, so let's go switch back over to the PowerPoint. So next is I'm going to use 2D simplification. So the reason why you'd want to do this is, of course, to get a finer mesh. The finer mesh we get, the closer we get to an actual, you know, real world value. And so we can section this guy. This is kind of a nice way to run a high-end mesh and get really good results. But again, you have to kind of make some assumptions as far as where you're going to go on that. So let's go ahead and close out of that. So here I have a little baffle, a little expansion joint, and I've already gone ahead and chopped this guy in half. So of course there's another flange on the other side of this, and I have a configuration that shows, so here's the default with both of it, and I went ahead and chopped this guy in half. So not only can I chop this guy in half, but I can also do 2D symmetry. So let's take a look at that. So if I do a new study, say for instance I want to do thermal. Now this is not with the SOLIDWORKS Premium, this is going to be with the simulation product. So Simulation Professional and Simulation Premium. So there's a little checkbox down here, use 2D simplification, and you just hit OK. When you do that, SOLIDWORKS is going to pull you to a little wizard. So it makes it kind of nice. So how do you want to use this? Do I want to use kind of an extruded or an axisymmetric? how do I want to actually slice this guy up? So I'm going to use axisymmetric, and then the section plane. I've got a plane right there, that front plane. So that slices halfway through there. So that looks good. And then I do need an axis because I'm telling it where the axis is symmetric about. So I'm going to select on that guy. When I do that, you'll see a little preview up here at the very top. Now, if this wasn't the one I want and it wasn't exactly symmetric, then I can check the little box for use other side, and you'll see the profile moves down to the bottom. So I'm going to flip it back to the top. I'll go ahead and say OK. And so now what's happened is it's taken a cross section of that, about that expansion joint. And now I can do analysis just on this as if it were kind of like a 3D part. So if I need to make connections or fixtures or forces or anything like that, in this case it's thermal, so I would actually put some of that information, on these edges and stuff. Now I've already got one kind of started up, so let's go to this guy. And let's go ahead and run it. So this runs pretty quick. And on this is a thermal analysis. So I actually have a high temperature inside here. And you can see it's a metal, so it goes right through the thickness of the material. So it's really quick. And then I have convection, and convection is actually going from the metal out into the air. So that way we can eliminate some of the heat, from inside going out into the atmosphere. So then, of course, you can see the thermal temperature going from the inside of the flange going out to the outside. So that works out pretty good. So with this, we can also go to a thermal stress. And I've gone ahead and got that ran. So this is actually the stress. So the tricky part about this, let's go into the properties, is the information is actually coming from the temperature or the thermal study. So wherever it's hotter, of course, it's going to want to expand. Now on this thermal stress, it's going to want to expand, but then I've also told this guy to move. So once I bolt this thing in, I actually shrink this guy up. So I've gone ahead and accumulated for that as far as I've got a 4 millimeter difference from the reference geometry right here where it initially starts to its end. So if we take a look at the animation, you can kind of see it's from its initial position going to its final position. Now this deformation scale is about 5 times. And you'll notice that I do have symmetry over here on the right hand side, which is keeping that guy, in this case, moving about the X direction. So those nodes can't move left and right. They have to stay along that plane. All right, so 2D simplification, again, main reason for this is we want to be able to get a really good high-end mesh. So I'm going to go ahead and turn on my mesh. So you can see I've got a really fine mesh. This is a really thin part, and I've still got 4 elements through the thickness of that thing. If I were to do that in 3D, this would have millions of elements. And SOLIDWORKS will do it, simulation will do it, but it's going to take a lot longer. This solved in just a couple seconds. If I did the other one, it would probably take about 20, maybe 30 minutes. All right, so use 2D simplification. Next, I'm going to go into some new tools. These are some nice little tips and tricks that are for 2016. So if you guys haven't upgraded yet, then please do. 2016, I've been very happy with its performance, functionality, and stability, really. All right, so let's take a look at this guy. So this is part of a little robot, and he has some really high torque values. So what I've done is I have done some mesh control. So in some of these little areas, you can kind of see the highlighted areas. I've meshed it to where it's pretty fine in those areas, and then of course the mesh control grows out to the other areas of the mesh. So one of the new features is, let me go ahead and double click this, it's going to take it a little while to load in, is we can section the mesh, and we can look at the quality of the mesh through a section plane. So in this case I selected on a plane, and where the plane slices through the mesh element, we actually see the entire element. So where the mesh elements are smaller, you'll see little small elements. Where the section plane slices through the larger elements, we of course see, looks like bigger mountains in the background. Okay, but what this allows us to do is actually look at the mesh quality through the thickness of the material. So we didn't have that ability. Now, in 2016, we also, a couple of the other nice little buttons. We've always had the ability to do a section on the stress. So I'm showing a von Mises stress. So I can right click and do section clipping. So we've always had the ability to do that. That looks really nice and smooth. But now we have a little option that we can show the mesh on the section plane. Now, since the section plane is slicing through the mesh elements at weird angles and stuff, what it does is it just superimposes that mesh onto that flat plane. So that way we get a pretty nice little section of what that thing looks like, and we can kind of tell what it looks like. Now, if you want to actually see the 3D, then we've got a button for that as well. So if I right click on the stress value, this is the new button in 2016. It's called mesh sectioning. So select on that, give it a second to load in. And then I like to actually show the mesh edge, so that way I can see all the different little black lines in there. And so kind of same thing on the mesh control. I can see the colors of the von Mises stress. So I'm actually looking at, again, the averages of each of the different nodes, and they're color coded depending on what the stress value is. So that's a really cool little tool. That's pretty nice. Some good functionality. All right. With that, we'll go into reference geometry. So a nice little thing, this is going to be a nonlinear study. So this is our high-end nonlinear package. Whenever we're doing a lot of plastic parts or O-rings or even some metal seals where the metal is actually bending a lot, we have large deformation, then we have to use the nonlinear package for that. And that's our high-end package. If you go to the SOLIDWORKS website, let's take a look at that. They have a little matrix here that tells you the different functionality that you have and what package it actually gets into. So our top of the end SOLIDWORKS product is kind of the standard. And then we have a simulation professional and a simulation premium. So if you're just doing single part assemblies or static analysis, then you could do that with just your SOLIDWORKS premium. But then to get buckling, static or drop test, frequency simulation, that's going to be professional. And then some of the nonlinear stuff is going to be in premium. So nonlinear and dynamics. So let's go take a look. So I've got this little buckle, and I've got a plastic part. So it's going into a metal part. The metal doesn't want to move. So this little piece right down here is my piece of metal. And then the rest of this is all plastic. So of course, what you have to do is push this guy in. So let's take a look at how we set this guy up in SOLIDWORKS. So I've got a 3D part. And of course, it's going to run faster if I do 2D simplification. So I've already got a nonlinear study that started with this. So that looks pretty good. So I've got a couple things. So the setup on this, I am using Symmetry on here because I've only modeled half of it. So it's symmetric about the top. I do have reference geometry, so let's edit this guy. So in this case, what I need to do is I need to push the clip in. So this line or this edge right here, instead of putting a force on it, I'm going to tell it that there's a displacement. I'm going to say, hey, this line has to move over to the left 27 millimeters. And so, but then I also need to pull the clip out. So to do that, we use a variation with time. So I'll go ahead and view the little curve here. So in the graph, at 0 seconds, it just sits there. And then at half a second, it gets fully pushed in. So it gets pushed in to 27 millimeters. Then I'm going to hold it there at 27 millimeters for a little while, 0.25 seconds. And then from 0.75 to 1 second, so a quarter of a second, I'm going to pull that thing back out. So I'm actually going to pull it out pretty quick compared to how much I push it in. So we could actually do that with 2015. But here's the new thing in 2016. So this little point right here, he's actually pushing upward. So on my clip, I have to use my fingers to actually push the clip up. So in this case, I have to put a little reference geometry, put a little vertex on there. And I'm going to do the same thing with time. But in this case, I could actually turn the entire feature off. So I'm not even going to use it right now. So I'm just pushing this guy in, just like I can't really, have no fingers there. So I'm just going to push it in. Once it pushes in and clips, then I'm going to go ahead and turn it on at 0.61 seconds. So that's going to push it up. Once I push it up, it's going to start to pull back a little bit. After 0.5 seconds, it's going to start, or 0.75, it's going to start pulling back. So you can see at 0.7 seconds, I'm going to go ahead and, or 0.77, I'm going to go ahead and turn it back off. So we'll see it start to drag across there. So that's a nice little cool thing. So let's go ahead and take a look at the stress results. And we'll go ahead and animate that. And I'll go ahead and zoom in. So you'll see this, the max stress is starting to change. The plastic is starting to bend a whole bunch right here. We're also getting some contact pressure, and then it's going to drop. Then I turn on that reference geometry. We're going to push it up. We're still getting some more stress here. And then I'm going to drop it, and you see a little bit of stress coming back down through there. So this is a really good technique because I'm starting to get not only pressure contact and stuff, but it's almost like motion and simulation at the same time. So that's pretty cool. All right, my last little tip and trick is playing with underconstrained bodies. So we can see how we can do some stuff with that. So that's always kind of a bit of an issue. So let's, I'm actually going to start from scratch on this real quick. And I'm just going to sketch on the front plane. So here's kind of the issue. I'm going to do a spline and just draw a straight length spline right there. Looks good. And if, say for instance, this is my part file. And in my part file, if I put a force on it, if I put a force up, it just moves the entire thing. If I put a force down, it moves it. If I push it right or left, it's just going to move the entire thing. So what do we have to do when we're doing a static analysis is we have to lock. We have to fix something in space. Since I'm on a 2D plane, I'm going to fix that. And the other thing I'm going to do is this little point right here. I'm going to go ahead and make that horizontal relationship. So now what happens is this guy is fixed in the X and the Y. He can't move. So now when I start to drag this guy, you can see I'm starting to put some type of a force along the entire system. So that's the whole issue is sometimes when we get to an assembly, I need to make sure that every component is fixed depending on where my fixtures in X, the Y, and the Z, and rotations about the X, Y, and Z. So once I can do that, then of course I can put a force or a pressure or a reference geometry to just move it. And when I do that, then I get to start seeing where the transitions and the issues are coming in. So let's go back to this part. So I've got a little structure here, and I've already kind of started up I've got a load and stuff on the very top, and then down here at the very bottom, I've got some fixtures and stuff. So those are locked into space. So when I try and run this guy, so let's go ahead and just run it. And I'm going to go a little bit over on time, probably about 4 or 5 minutes. But this should be good stuff. All right, so I get a little issue. It says, hey, the model's unstable. It can't figure out where something is under constraint. I know at the bottom, I've fixed these guys in the X, Y, and Z, but then some of the other components, not sure exactly where they're constrained or not constrained. So one of the new little buttons that we have is when you go into your contact visualization plot, we have a little tab for underconstrained bodies. So when we go ahead and calculate that, and it'll take it a little while to do, it's going to find out, it's going to say, okay, here's your locked position, and then let's go see if the next component next to it is locked. Is it bonded to it or not? If it's not bonded, then it can move in the X, the Y, and the Z. So give that a second, it's just about done. So if I click on one of these guys, you can see it highlights it, and it says, hey, this guy can move, in this case, the X direction. Well, guess what? That same guy can move in the Y direction. And he can move in the Z direction. And you can see that he can rotate about the X, the Y, and the Z as well. So we've got an issue where that guy is completely not constrained. He's not connected to anything else. Well, look at, I've got a whole bunch of these groups. So that guy's not doing it either. He's out there. So it looks like my structure up at the top and bottom, the columns are fine, but it's all these members in between that are bad. So this takes a lot of work out of having to go dig and find out which parts and stuff are under constrained or not. So I forgot that when I modeled this guy up, I put weld gaps in here between the columns and the beams there. That's easy to fix in 2016. All you have to do is edit it, and there's a new button in here for non-touching faces. So if a node element is, in this case, within 2 millimeters of another node element, then it's going to go ahead and make those guys bonded. This is only for bonded contacts. So with that in there, then we can go ahead and run it. So two really nice little features. One to show the visualization of whether stuff is constrained or not. And then two, the ability to, if they're not completely touching, because maybe I have a weld gap or something like that, then I can make sure that that works and functions. All right. So the main thing here is I can see that all of my beams and columns and members and stuff are starting to take stress. They're all moving at the same time. So I know that the bonded contacts are working. Everything's functioning in there. I don't have a part that's just kind of flying out in space somewhere. So that looks pretty good. All right. So hopefully you've enjoyed that. If you have any questions, I'm going to leave the question pane open for just a little while. If I don't get to the questions, sometimes I'll email them to you. And if you have the questions, of course, we have the answers. Don't forget, I do have one other little thing. If you're looking at purchasing SolidWorks, we have a promotion that's going on. It's a buy one SolidWorks product, get one for 50% off on the second SolidWorks product. So if you want to take a look, get a hold of your salespeople, they can help you with that. So next week, November 13th, next Friday, we're going to take a closer look at the SolidWorks Toolbox with Shane Colvin. And so that should be a pretty fun little demonstration. So I'd like to thank you guys for coming out. If you have any questions, again, put it over to the question on the console. And thank you for your time.